Thanks, Arun, for the nice introduction. Welcome, everyone. I will be focusing on controller challenges, controllers which are actually implemented for some of the advanced serial links. And to get into more details, initially I will be just going through typical advanced link implementation, which will show PHY as well as controller part. Then I'll get into the challenges which controller has to face, because there are a lot of things which are happening as once you move from lower line rates, baud rates to higher baud rates. And then I will cover some of the advanced serial link controllers which we have in our portfolio, and we have done interoperability with, for example, with the Rambus PHY. So that's how a typical advanced serial link implementation would look like. Lower part, which is shown here as SerDes, would typically be having PMA, PCS layers. And the controller part, which you see on the top, is going to have MAC, data link layer, and transaction layer. And application interface could be custom, or it could be something which is standard. For example, it could be AXI or AHP. That's how a IP is going to be provided. And then for a full SoC implementation, this is going to be terminated into any other bridge or memory or a processor interface. So, but as far as the serial link is concerned, you can see them as a PHY and a logical layer. So today there are various standards which are there in the industry. PCI Express is one, RapidIO is another. And if you look at any of these standards, the specification is defined nicely across all the standards in a layered manner. And each of the layer has specified a very clear function. And what it allows is that you can actually move towards new generation without really impacting the other functions. For example, if you're just increasing the baud rate, you can just change your PHY layer and say some of the MAC layer functions, but the rest of the layers are still there. So it's not that you are redesigning the whole thing. So it's very important for some of the interfaces, standards to maintain legacy. It's a must in some of the cases. And in some of the cases, it's desirable to maintain the legacy. And just for the naming purposes, I think PMA is something where you will be doing clock data recovery, serialization, deserialization of the data. You have the analog front end, PLL. PCS is the layer where it's a digital part, but you would be doing encode, decode. Various type of mechanisms are used in the industry, starting from 8-bit, 10-bit to 128, 130, 64, 67. And then you will also be having elastic buffer function there, because there will be PPM differences between the two link partners, and you want to make sure that you can manage the PPM differences without having issue with the protocol itself. Then you have the MAC layer, which it's a guaranteed delivery of the data. That's what the data link layer does. And then the transaction layer, that's where you will be doing the quality of service. You will be ensuring that there is no deadlock in your fabric. It's not that the link partners are waiting for responses from the other side and the fabric is not moving any progress. So those are the functions which typically are very well defined within the spec if you look at. And controller needs to make sure that it can implement these functions along with PHY. So moving to the challenges, we are looking at, if you're familiar with current generation, the serial link interfaces are generation 3, where you can see 8 gig or 10 gig type of implementations. And the next generation, we are looking at 16 gig or 25 gig for the controllers we have. And once we are moving towards these higher baud rates, there are basic challenges, which are basically the signal transmitted over a link is going to be degraded by the losses, and the characteristic impedance discontinues in the media. And again, these losses are going to be more with the increasing baud rate and media length. So typically specs are going to define short reach, long reach type of specification, so that you can have different design if you want, based on what is your target market. And again, because of these losses, it's very hard for the receiver design to make sure that it can actually successfully recover the data. So now, how you make sure that you can actually upgrade to these higher baud rates is by doing sort of adaptive equalization, where you are actually tuning your link partner's transmitter coefficient based on your operating conditions. So there has to be a protocol modification where you can actually tune your link parameters based on the operating conditions, the signal length, the variation in the transmitter impedance. You can still meet the BER, bit error rate, specified in the specification to make sure that you can successfully carry a protocol over it. So there is what we refer to as adaptive equalization and training. This is something which every specification from Gen 3 going to Gen 4 has to adopt, because at these baud rates you can't assume that the fixed values in your PHY are going to work across all the operating conditions. So adaptive equalization training is something which controllers need to look at and make sure that they can actually implement these correctly across various PHYs. So there is some handshake required, I'll cover, but this is one of the major things which we need to look at while designing the controller, how you actually do the equalization and training, even though those functions are primarily residing inside the PHY. And of course, with these higher baud rates, you are getting more bandwidth, and now you have to handle that much bandwidth in your logic layer. You have to now deal with the higher bandwidth. There may be challenges where you can't run your full design at that higher clock rate, so you may have to widen your data path width, for example. So you need to look at latency, you need to look at the bandwidth, you need to look at the trade-offs, and also you want to make sure the interface which you provide to the user logic, where a full SoC implementation is going to use this IP, you want to keep some sort of a legacy so that not the full SoC design needs to be changed just because now you are transitioning from Gen 3 to Gen 4. Basically what AET is doing is trying to tune the transmitter coefficients of the link partner. You are actually going to be, controller needs to understand AET commands when the link partner is sending those. Those commands are going to carry the coefficients which you are supposed to set on your TX side. This is a protocol level function. So you need to understand those equalization commands, the AET command, and inform that over to the SerDes so that SerDes can set those values. Similarly, the controller should be able to issue these commands so that the link partner's PHY can set its transmitter coefficient, and then you can implement the mechanism so that on the receiver side you have the figure of merit or some sort of mechanism to see what is your bit error rate, and that's how you are going to be tuning. So the challenge as far as the controller is concerned is in some of the interfaces, specifications, there is a very well-defined interface between controller and PHY. You don't need to do any custom work. But in some of the advanced serial link interfaces, there is no such interface defined. There, you have to do a design where there is a very minimal effort when you are migrating from one PHY to another PHY. So there is a challenge as to how we have to deal with various PHYs and ensure that we can manage and implement AET, because this is very important. You have to have AET implementation. You can't assume that one fixed value is going to work across all the operating conditions. And as I said, the additional challenge is to handle higher bandwidth. Now we have higher bandwidth. So just to give you an idea, for Gen 1 and Gen 2, which were typically 2.5 gig, 1.25 gig type of baud rates, most of the designs were using 64 or 128-bit data path, because those data path widths were good enough to ensure or handle the available bandwidth. Going to Gen 3, which is Gen 2 was 5 gig, 6.25 gig. Gen 3 is where we are running at 8 gig or 10 gig. There we have to move from 128-bit to 256. And Gen 4 definitely would require 256-bit to 512-bit data path implementations. So not only you have to increase the data path width, and this is a big effort because it's not just widening the data path. There are other challenges, because if you just look at it, if you have a 128-bit data path, typically given a packet size, smallest packet size, in one clock you would be getting one packet. But once you move to 256-bit or 512-bit data path, every clock you are getting that much wide data, you will be receiving more than one packet in one clock. So what it means is the complexity is increased, because now in one clock you are dealing with more than one packet. And there is more complexity which gets increased just because you have to handle a wider data path width. And the data buffers, there is in the serial protocol, typically for you to have the guaranteed delivery of the data, there is some sort of a handshake. Transmitter keeps on sending the packet knowing how much buffer space link partner has. It's called a credit-based mechanism where the receiver sends you credits, transmitter, the sender keeps on sending those many packets without worrying about whether the packets have been received successfully or not. And then by the time he is done with the last packet, he should have received the credit back so that he can push the next packet. So there is a credit handshake. And if your buffer sizes are not big enough, you may be blocking, you may not be able to use the available bandwidth in the link. So I have few slides to indicate how or why that is important. As I talked about this credit handshake, what is important is the round trip latency. You have these functions, MAC, data link, transaction layer in the controller. You receive the packet, you consume the packet. Once you have consumed the packet, you again send the credit back to the link partner. So there's a round trip latency, receiving of the data, packet, making sure that the packet is good, and then informing the link partner back that I am done with the packet, you can again send me next one. This example shows that one of the implementations, which is a wider data path width, 256-bit, running at 125 megahertz, and if a typical case we take of a latency of 20 clocks is going to be consuming 160 nano. So this is the round trip latency where the link partner is going to take this much time before it can inform you that the next data can be sent. Whereas if we look at the 128-bit 250 megahertz implementation, the same latency now translates to only 80 nanoseconds. So this has an impact based on which design you are using. And this is what is shown here. So suppose on the left side is where you are doing the design which is actually having 160 nanoseconds, and the right side is your link partner which is trying to push packets. It is pushing the packet, and then the responsibility is your implementation to give the credit back to the transmitter so that you can see the back-to-back packets. Means the round trip latency is 160 plus 80 nanoseconds, assuming link partner is pretty good, 240 nanoseconds. So you can see that at least you need to have 5 packets in your receive buffer, because the credit updates is going to take close to 240 nanoseconds. And if you have less than 5 packets, what will happen is there is going to be dead time here on your transmitter. The transmitter won't be able to push the packet. So if the receive buffer size is small, even though your design is good, you will not be able to use the maximum bandwidth. Whereas if this is a 80 nanosecond delay on your implementation, it's only going to take 160 nanosecond now, because 80 nanosecond on your side, 80 nanosecond on your link partner. So in this case, you can have a smaller buffer size to still utilize the bandwidth to the full possible available. What does it tell us as far as the controller is concerned? That we have to design something where the receive buffer size, for example, is configurable in size, because given a condition in terms of which technology we are implementing it at, we may have to implement it in 128-bit data path width or 256-bit, because depending upon whether it's going to be a faster technology or it's going to be a slower technology. So the controller has to make sure that the receive buffer size is configurable so that it can meet the available bandwidth and it can accommodate that much bandwidth. So this is important for us. It poses a lot of challenges, because now you have to make sure that a different buffer size, still your design is good. Given that, I have few slides on some of the offerings we have. So we have a PCI Express controller IP. The good thing about PCI Express is that there is a very well-defined interface between PHY and the controller called pipe. The interface is, our core is compliant with the pipe. We implement MAC, link, transaction, as well as application layers. So this is where we add some of the functions and provide AXI interface towards the SoC. And it also provides the DMA function. The good thing is that we have configurable data path width, again, to handle various implementations, provide the AXI interconnect for easy integration into an SoC, and the pipe, which is compliant. We can transition across various PHYs and still see that it works. And the AET is also handled pretty nice. The other core we have is RapidIO. This is another interconnect primarily used in base station DSPs. They have the RapidIO. It's a low latency fabric interconnect. But it doesn't have a very well-defined PHY controller interface. As you can see, there is a SerDes interface shown here towards the bottom, which is not standard. So here we have to deal with the challenge we talked about in terms of how to deal with the AET, because now you have to have some sort of an interface which you have to define so that you can carry over information in the AET command to the PHY partner. Similarly, you can receive the data back from your link partner when you are trying to tune its transmitter. So it poses a challenge, but this is another challenge for us. We have to deal with it and define an interface which may be useful across various PHYs. And the code itself has PHY transaction layer. The application layer, again, because it's a fabric interconnect, it has much bigger landscape in terms of features it supports at the application layer. There is a streaming where you can actually do the segmentation reassembly of a bigger Ethernet packets on a smaller fabric packet size. It has a messaging where it's an addressless data push mechanism where you can push packets into address letters. You don't really need to know the address space of your connecting node. So messaging is supported in addition to the standard DMA where it's an address-based mechanism where you actually know the address space of your node you want to push the data out. So application layer is much wider, but again we are providing AXI interface so that it can easily integrate into a SoC, having other modules also using AXI fabric. Additional advantages we do is, again, these IPs, by the way, are available. They have been used in silicon for a number of years. So we have a pretty wide customer base and successful silicon in the market. These we participate and align with how specification is evolving. We actually update our IPs as well. Provide I think the superior technical solution, because this is something which we always claim that the features are pretty wide and most of the things specified in the specification are covered. Looking at various technologies, the core needs to get in. And we have partnered with PHYs, like Rambus is our PHY partner, as well as the IP providers, because there is a verification IP involved to do the SoC level verification. And we go through all the certification process. This is also very important because these standards also specify some sort of a compliance and interoperability testing. You have to make sure that your solution is going to be compliant with the specification. So we take our IPs before we actually make it available to our customers, that those are compliant, they are interoperable, and so that the customer's implementation is also going to work in a system. So that's it.